Exercise 6 next. So we are again, the kind of problems that we were solving, we are again given that a and b are two integers such that they are relatively prime, that is their greatest common divisor is 1. We then need to prove that the GCD of a plus b and ab is also equal to 1. So we start off by giving this GCD a name. Let D be the GCD of a plus b and ab. Then, because it's a greatest common divisor, so it's after all a divisor of both the numbers, both the integers. Then D divides a plus b and D divides ab. Now from these two divisibility relations, we are now going to conclude something. So we have D dividing a times a plus b minus ab, because D divides this integer and D divides ab, so D will also divide this combination, which however is equal to, because ab and minus ab will cancel out and we will be left with a square. So D divides a square, and a similar calculation gives us this. D also divides b times a plus b minus ab, which is b square. So D divides both a square and b square. So D will also divide the GCD of a square and b square by the properties of GCDs. Hence, a square and b square. This, however, is equal to 1. And that follows from a previous exercise that we already have solved, and that thing is this. In fact, from the previous section itself, we are having that exercise. Exercise 20 part F of section 2.2. This is equal to 1. So D divides 1. But D is the GCD of some integers, so by definition D is a positive integer. And when you combine that with this divisibility relation, you get the conclusion that D has to be equal to 1. Because if we don't say anything about the sign of D, say D is any non-zero integer that divides 1, then we know that there are two possibilities. D can be minus 1 or plus 1. But along with this, we have positivity also, so D has to be equal to 1. Since D is positive, this implies D is equal to 1, and that's what we wanted to show. So here the solution ends. Next, for non-zero integers, a and b verify that the following conditions are equivalent. Three conditions are given where we will have to prove that any one of them implies the others. And the conditions are these. Condition A is the statement that A divides B. Then condition B is the statement that the greatest common divisor of A and B is the absolute value of A. And condition C is the statement that the least common multiple of A and B is the absolute value of B. Okay, so the way we are going to write the solution is just this. We are going to show that condition A implies condition B, then B implies C, and C implies A, so that there is a cycle of implications, and because of which if you start anywhere in that cycle you can reach the other two conditions. You can simply see that is true from the structure of this implication that now we are going to prove. Okay, so let us start. We first assume condition A, i.e. A divides B. Okay. Now, should I write like this, or let me just write the immediate consequence of this divisibility. This implies the absolute value of A also divides B, and also at the same time, although not related, but we will need to consider these two things together. So I am writing also, after putting a semicolon, that the absolute value of A divides A. Okay, let us now see how this one is following from this. It's not very difficult to see why. A divides B means what? B is equal to AC for some integer C. Now it is given that A and B are non-zero integers, but not necessarily positive. Any one of them can be negative also. Now if it happens that A is actually positive, then this is equal to this. If, or I can just simply write like this, if when A is positive, then AC equals the absolute value of A times C. But when A is negative, then the same AC equals absolute value of A times minus C. Do you see why? When a is negative, absolute value of a will be minus a by definition. That minus a and minus c would give us ac. So we see that in any case, b actually then is an integer multiple of the absolute value of a. Now because our a is non-zero, so absolute value of a is also a non-zero integer. In fact, it's a positive integer. So this tells us that in any case, the absolute value of a also divides b. Since it's very easy to see why, so we are not showing it actually in the solution itself. And in a similar manner, the absolute value of a also divides a. And you can almost see, I hope you can almost see why. See, a can be written as the absolute value of a if a is greater than 0, and when a is less than 0, you have this. So just like this one, a is always an integer multiple of the absolute value of a provided a is non-zero. Well, when a is 0 also, that is true, but that's not what we are considering here. So these equations tell us that this divisibility relation is also true. Okay, but these details we are not going to make parts of the solution. So we just omit them. We have understood how they come, where they come from, and that's enough. Okay, so we have got what? So this divides a and this divides a. Okay. Okay, now in order to show that the GCD of a and b is in fact equal to the absolute value of a, we need to show something else. We have got one part of the definition of GCD. If you go back to the definition of GCD, this will be the GCD of a and b if this is true and then something else is true, and that something else is the condition that if you consider any divisor, say d of a and b, then that d also has to divide this absolute value of a. If you manage to show that, then you can conclude that the GCD of a and b is in fact equal to this. So let's just show that now. Next, let d be any non-zero integer satisfying these conditions, that d divides a and d divides b. In other words, d is a common divisor of a and b. Okay, now we are going to consider something else. We are going to consider the opposite relation, opposite to this one here. Since a divides the absolute value of a we thus have d dividing the absolute value of a. Now I have to explain why these things are true. First of all, where is this coming from? You can almost guess like how we justified this divisibility relation. A similar justification can be given for this one also. However, still if you want to see why, this is in fact even easier to see than the justification of this. That is because the definition of the absolute value of a itself tells us that whatever we have written here is true. Because by definition we have this, no? So this integer is an integer multiple of a in any case. Whether a is positive or negative, it does not matter. In each case, it's an integer multiple of a. And because a is non-zero, so a divides this. Okay, so we understand where this thing is and why this thing is true. But now, then how does this imply this? This is not implying this alone. You combine this and this. That is, if you see, d is dividing a and a is dividing this. Because divisibility of integers is a transitive relation, so d divides this, and that's how we are getting this. Okay, so now we have both the parts of our definition for GCD, and so let us just see once more what we have shown here. We have proved that this integer mod a, if I want to call it mod a, absolute value of a is a common divisor of both a and b, and any common divisor d of both a and b divides this one. So that means by definition this is the GCD. Hence we have okay, so that means we have managed to show that a implies b. Next we assume b and then show that c follows, proving that b implies c and then c implies a. Okay, now this, we need to prove that the LCM of a and b is equal to the absolute value of b. So this is where we recall a result which connects LCM and GCD. We have already got that in theorem. What was the theorem number 2.8? I think 2.8. By theorem 2.8, this times the LCM of the absolute value of a and the absolute value of b is equal to this. But let us note one thing carefully before we move on, that we have been able to write this because both the integers here are positive integers. If you go to the actual statement of this theorem, there you will see that the theorem works only for positive integers. Now why are these things positive? That comes from the hypothesis that a and b are non-zero integers. Okay, so that is why both of them are positive. Yeah, now we move on. Now we write whatever we want to write next. So this times LCM of A comma B equal to this times equal to this. Of course we understand, this is what we have written here. However, what is this? What is this first equality? How are we replacing A and B with their absolute value counterpart? That is because if you go to the definitions of GCD and LCM, you will see that these integers have been defined to be positive. Because of that, I in fact have already discussed about it before. For GCD, for LCM I didn't say this, but the same is true for LCM also. So what I am trying to say here is this. Let me just first wrap these things up, then we can explain. So what I am saying here is this. If A and B are, say, like how we have here, A and B are non-zero integers. For the GCD to exist, however, only one of them needs to be non-zero, but we have both of them non-zero. So that's not a problem. Now, if you go to the actual definition, the definition of GCD, you will realize that the signs of the numbers do not matter. Okay, I'm not going to say anything more about this. You go to the definition of GCD, and there, because these things look quite abstract, you try to convince yourself that, say, the GCD of 2 and 4, or if you really want to take something non-trivial, the GCD of 6 and 4, we already know that it is 2, but that is also equal to the GCD of minus 6 and 4, for example. You try to see why this is true. You will, I hope you will understand. There is no doubt you will understand. If you have understood what GCD is and how GCDs work, then you will definitely understand this, that the signs of the numbers of which we are calculating the GCD, they do not matter. So that's what we are using here. It does not matter whether A is positive or negative. It does not matter whether B is positive or negative. We can consider the positive counterpart. That is, say for example, you have this equal to A, this equal to B. Instead of considering this, we are considering this, which is equal to that one. And similar equations are also true for LCM. Again, because of similar reason. LCM, just like GCD, is by definition a positive integer. That is why. Okay. Now we can use our hypothesis. What is our hypothesis in this part? In this part, our hypothesis is this. That means here we can put absolute value of A. Thus, the absolute value of A times LCM, of course, is there. This is equal to this, or Now you can cancel absolute value of a from both sides. The reason is that your this is non-zero. In fact, this is a positive integer. So that's how you get your final conclusion that LCM of a and b must be equal to the absolute value of b. So here you have proved that part B implies part C. Now finally, let us prove that part C implies part A. Next, assume, that means we have to start with this one as our hypothesis. This. And B, what is our part A? Part A is the statement that A divides B. Okay. Now LCM of A and B is this. LCM is what? LCM is the least common multiple. Among all positive multiples of the given numbers, LCM is the least one. But after all, it is a multiple. That means both A and B divide this. Among them, we only need the first one. That is, A divides this. So this implies A divides this, which in turn implies that A divides B. Why? Just like before, you supply this other divisibility relation also, and then note that divisibility is a transitive relation on the set of integers. So you get this. I mean, combining these two, you get this, and that is just condition A. So we have managed to show that this cycle is true. This implies B, then this implies C, and then C also implies A. So you start anywhere, you can go to the other two. And that's how the solution is over. You can in fact write a final concluding line or remark that hence all the three conditions are equivalent to one another. That you can just simply write. So we stop it here itself. Next. This is a computational one. Find here we are being asked to calculate some LCMs. LCMs of numbers of which we have already been asked to calculate the GCD in the first exercise of this section. So we are going to use that and our theorem 2.8 to calculate the LCMs. LCM of 143 and 227, then LCM of 272 no, that's not, I mean, I can write the last one here also, but 306 and 657, and there is another one, and here we have 272 and 1479. So the solution simply goes like this. From the solution to exercise 1, the convention I am following in referring to these exercises or their solutions is that if you don't see an exercise followed by the section number where it is appearing, you should understand that it is in this section itself where we are currently at. So from the solution to exercise 1, these things we already know, or we have in fact calculated. The GCD of 143 and 227 is, I think it is 1. No? Yes. Then the GCD of 306 and 657 is 9, and $1,479 is 17. Since we have these calculations available in the solution to exercise 1, so we are not repeating things. But if you are solving a standalone problem, of course you have to show all the things. So by theorem 2.8, I am not really sure whether we should read these things as 2.8, theorem 2.8 or theorem 2.8. I am not entirely sure. Okay, I will see it later. So by theorem 2.8, LCM of 143 and 227, you know what it's going to be. It is the product of these two numbers divided by their GCD, which in this case is 1. And this turns out to be equal to how much? 32,400, and I just hope that these values are correct. If not, you can, of course, you are being requested to correct this. The next, LCM of 306 and 657 equals 306 times 657 divided by their GCD, which is 9, and this is 22,338. And finally, the LCM of 272 and 1479 is their product, divided by their GCD, that is 17, and this is 23,664. Okay, so that's just it. Next, let us solve one more. Prove that the greatest common divisor of two positive integers divides their least common multiple multiple. So the GCD of two positive integers would divide their LCM. In fact, positivity of both the integers actually does not play any role here, but in order for the LCM to exist, both the integers must be non-zero. So you can in fact modify this exercise by putting the relaxation that they need not be positive but they are non-zero. Still it will be true. I mean, the whatever is being claimed here, that will still be true. Solution. Let A and B be two positive integers. And let, for ease of notation, let D denote the GCD of them and L denote their LCM. Again, by theorem, then product of the GCD and LCM equals the product of the two integers. Now here of course I said just now that you can relax positivity a little bit by taking non-zero integers, but then whatever we are going to write here, we are able to apply theorem 2.8 directly because A and B are positive. There, however, if you do that relaxation, here you have to accordingly modify the things. So now D times L will be equal to AB. That means GCD of AB times LCM of A and B equals AB. This implies, okay, now our aim is to show that L is a multiple of D. So let us see how we can express L in terms of the other things from this equation. If I write A divided by D, I can write, and at the same time I am also writing B divided by D, but then I have written an extra D in the denominator, so I have to multiply by a D here. Now note that, okay, first of all, how are we able to divide by D? We are able to divide by D because D is a greatest common divisor. So by definition it's a positive integer. In particular, it is not equal to 0. So that's why we are able to divide by D. And one more thing that you can notice here is that because D is the GCD of A and B, D divides both A and B. So the things you see here which look like quotients, actually they are integers. So now we are going to mention that where A over D and B over D are integers, and within brackets we also write the reason, since D divides both of them. So you have shown that L is an integer multiple of D. Now because D, see, that alone is not enough to conclude that D divides L. Additionally, D also has to be non-zero. So I am just saying these small little things because we should see at all times we should actually exactly know what we are doing and why each step comes, I mean exactly how each step comes from the previous step. Let me just show you the thing that I was saying here just now. You look at these two equations and you look at a general equation like this, where A, B and C are integers. From this second equation, you can conclude that 3 divides 6 because 3 is a multiple of 6, an integer multiple of 6. But if we just simply stop here, then we are neglecting one more piece of information. 3 is not only an integer multiple of 6, but at the same time 3 itself is non-zero. So that is why 3 divides 6. However, here you can see that 0 is an integer multiple of 0. But we don't say 0 divides 0 because that divisibility relation has been defined only for non-zero divisors. Okay, so just this itself alone does not tell you that B divides C. Along with this, you also need B to be non-zero. Okay, but non-zero D, I mean of course D is non-zero. So we are just simply going to next write that this implies D divides L. But in the background that non-zeroness is working. Okay, without it we cannot go any further. We will have to just stop here. Thus, D divides L. If you really want to be absolutely, rigorous about these things, you should write, since D is not equal to 0, the above equation implies this. But anyway, we have now completed the solution. We have shown that the GCD of two positive integers divides their LCM. And let me just finish the video here itself. I think 3 more exercises are left from this section, which we will solve in the next number theory update, and then this section will be over. There is one more section in this chapter where we consider equations which look like this, where a, b and c are integers, and we ask ourselves whether such an equation has a solution where x and y are also integers. And in answering such questions, this theory of GCD will help us. Okay, so that the next section is about that. We will see those things. And the next video is of course again on coming Friday, and it will be about graph theory again. So with that, I wrap things up for tonight. If you want to say something about these things, you can use the comment section below, or you can mail me at my usual address. The link will be there in the description. So see you on Friday with graph theory. Minors and topological minors, I think we have already finished or not, I cannot remember. We will see. So until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.